Good afternoon. I guess it's time for Jesse to check whether he's getting a signal here from the microphone while he's, okay, thank you. Let's see, one little bit of business before I forget. Is Devin Belmar here? Just yes, no, just having communication problem with him last week. All right. So, Math 221 exam on Tuesday. And my view about preparing for exams is that sometime well in advance one takes stock of the material that is to be covered. And certainly in my class, I spent the last of the classes doing exactly that, giving an outline of things. But now, as the exam becomes very close, it's a matter of focusing on how to solve certain problems. And I think the best choice that I can make of problems, well, the best choice that I could make of problems would be to do the problems that are on the exam. But I'm not going to do that today. It's happened once or twice, but not the whole collection. But that's not my intent today. And so I think the next best choice is to look at problems from previous exams. And so the material that I've passed out is indeed those problems from the last several years' exams that cover the material that I've got for today, which is the last part of the course. The material on eigenvalues and eigenfunctions, Fourier series, boundary value problems, and separation of variable for partial differential equations, and the full partial differential equations problems. There's a few more handouts on the table there. And in particular, these are the problems of that material from the exams in semesters in which I was in fact involved. And one of the things, as we all get, as you do things, the problems are similar. For the most part, it is my intent to do the problems from the exam last semester, the 2015 fall semester. But I wanted you to have ones from other semesters. So let's see how. Let me see where folks are going here that are still in need of my little handouts here. Who else just came in? I saw a bunch in this row. Thank you.
Thank you.
Okay, take one. So we're also, there's some folks who need or want this handout.
Take an extra one.
Yeah, stacks and stacks. Take a few to the back. Plenty left. All right. Okay. Okay. So the first topic that I've selected here is the eigenvalue eigenfunction, and if you scan through these, you find the 1, 2, 3. The first four of these are pretty similar. The fifth one it was a little bit of gotcha that we do things every now and then to get a little bit out of the rut, and that semester we decided to use a Cauchy-Euler equation. That is not the case this semester. And so we have y double prime plus lambda y equals 0. The boundary conditions, y at 0 is 0, y prime at 1 is 0. And so with the eigenvalue problem, the objective is to find non-zero solutions for this problem, which is a homogeneous differential equation. The boundary conditions are also homogeneous, and so the fact that y equals 0, identically 0 is a solution, is so obvious that we call that a trivial solution, and the objective is to find others. And so the differential equation is constant coefficients. We write down the auxiliary equation, m squared plus lambda equals 0. M squared is negative lambda, m plus or minus square root negative lambda. In every case, the differential equation with constant coefficients leads us to the auxiliary equation being a quadratic. Second order differential equation leads to a quadratic, and the quadratic formula, or the solution of the quadratic, ultimately involves, when we have an arbitrary quadratic, involves the square root of something. The quantity under the square root is the discriminant, and the nature of the solutions is different depending upon whether the discriminant is positive, 0, or negative. Now, I know that one of my colleagues at least likes to do it in the other order, but I choose to look at the situation in exactly that order. So first of all, the discriminant here is negative lambda, the quantity under the radical. And so my first case is that quantity positive. To make it look positive, I like to write it as alpha squared, as something squared. And I can assume that that quantity is positive because the formula involves both a positive and negative values here. So m is plus or minus alpha. The solutions c1 e to the alpha x plus c2 e to the negative alpha x. So we are going to home in here on the boundary conditions. The first of them at 0, we have 0, so y of 0. Substitute that in is c1 e to the 0 is 1, c1 plus c2, that's 0, and therefore c2 is negative c1. The second of the boundary conditions involves the derivative, so I need to calculate the derivative. Y prime alpha c1 e to the alpha x minus c2 e to the negative alpha x. So I substitute x equal 1 here. I'm going to use the fact that c2 is negative c1. So negative c2, that's the same as c1. I'll factor that out. Set x equal alpha. It was negative c2 with c1. So I get that this combination must be 0. Alpha, by hypothesis, is not 0. The exponential function is non-negative. So the sum of two exponentials, that's a positive quantity. It's not only not 0, it's in fact positive. So is alpha. And therefore, two of the things in the product are positive, and therefore C1 is 0. And then C2 being negative C1 is 0, and we have only the 0 solution. So the second case is discriminant equals 0. The differential equation then is y double prime equals 0. And so solution C1 plus C2x. Applying the boundary conditions at 0, get C1, that's 0. The derivative is C2. So y prime at 1 is C2, that's 0 only. And again, only the trivial solution. So the third case is the discriminant being negative. And just as when it was positive, I wrote it as alpha squared. When it's negative, I like to write it as negative alpha squared, so it really looks negative. M is then plus or minus square root negative alpha squared plus or minus alpha I. And so this is the third kind of solution for the differential equations. It's the case where we have sines and cosines. C1 cosine alpha x plus C2 sine alpha x. At 0, I have C1, which is 0. The derivative C1's gone, so the derivative is just the derivative of C2 sine alpha x. Alpha C2 cosine alpha x does that. So y prime of 1 alpha C2 cosine of alpha times 1. So for that product to be 0, alpha is not 0 by hypothesis. The objective is to find solutions with C2 not being 0. And so for a non-trivial solution, cosine of alpha must be 0. And so alpha must be one of the quantities which gives the cosine 0, and these zeros of the cosine occur at odd multiples of pi over 2. I like to write I tend to write odd numbers as 2n plus 1. If you want to write it as 2n minus 1, that's the same thing. It's just a question of where you want n to start. I started at 0. So that's alpha. Now, having done all that, I better go back and look and see what the problem said. It said find eigenvalues and eigenfunctions. Eigenvalues are the values of lambda that make this whole thing give non-zero solutions, not alpha. Up there at the top, lambda is alpha squared. So 2n plus 1 times pi over 2 squared are the eigenvalues. And the corresponding functions, solutions. The solutions come from y, C1 cosine plus C2 sine. C1 went away, so we're left with the sine as the solution. It's sine of alpha. Alpha was 2n plus 1 times pi over 2, an x in there, and And so we get the eigenfunctions as the signs with the appropriate value of n. So that's the procedure in general. The case with the exponential solutions, by and large, it does not give an eigenvalue. The case of zero discriminant, lambda equals 0, gives eigenvalues, especially when we have both of the boundary conditions involving derivatives. And but the golden part of this, the place where most of the eigenvalues and eigenfunctions arise, come from the negative discriminant, the solutions which involve sines and cosines. So that's that. Questions or proceed? Okay. Fourier series. One of the things you will notice if you browse through, especially page 3, is that all of the Fourier series problems that appear there involve either the Fourier sine series or the Fourier cosine series. The syllabus changed in this course changed slightly in the last year. We dropped one topic and expanded Fourier series a little bit. So last semester, we actually had 2 problems on Fourier series. The first one, consider a half-range Fourier sine series for a particular function. 1 minus x, and asked that we plot that the students plot the function to which the Fourier series for this converges. So Fourier series, we'll get to sine and cosine. We'll get to the full series in a moment, but the Fourier series comes in 3 flavors. One represents a function using both sines and cosines. So a0 over 2, 1 to infinity, a sub n cosine n pi over lx, b sub n sine n pi over lx. And this requires f be defined on a symmetric on an interval, typically from negative L to L. So that is an interval of size 2L. The width of that interval is 2L, and the functions involved here are periodic with period 2L. The period matches the range of the function. The other series, the sine and cosine series, which basically throw away one of the other piece here, the sine series. The sine series gets rid of the a's, and the cosine series gets rid of the b's. In both cases, these are sums of the component functions from before. These are functions whose period is 2L, and yet these come from a function which is defined only over half the period. Some people, including some of my colleagues, like to call these half-range series. Because we start with a function which is defined only over half of the period, so to speak, the range of the sine or the cosine functions. So this problem, problem 5 of last year's exam, which takes 1 minus x, is one of those. It's an interval only from 0 to 1 for which the thing is defined. The first thing that one notices here is that the statement of the problem tells us the value for L. In this case, L is 1. The question's about sine series, the Fourier sine series, and we want to know where it converges. Okay, so the point about a Fourier sine series is this. We're supposed to plot this thing from -2 to 2. I'm going to go, in fact, to a little bit larger, to 3. Okay, so Fourier sine series. The idea is that in the interval where the function's defined, if it's continuous, it converges to the function. The function 1 minus x between 0 and 1 the graph is a straight line of slope -1 at x equals 0, f is 1. Nextly, a sine series. Every term that's involved in a sine series is an odd function. The sum of a Fourier sine series has to converge to an odd function. And so the period is, in fact, from -1 to 1. We have to have an odd function between -1 and 0. And so we reflect this thing, and we get this function. And now the Fourier series sees something which, as it approaches 0 from the left, wants to be -1. From 0 to the right, it's +1. The Fourier series is going to converge to 0. And in fact, you can see that right away. You said x equals 0. Every term in a Fourier sine series is 0. A Fourier sine series has to converge to 0 at x equals 0. It makes no difference what the original function is. The Fourier sine series, once we get outside the interval from 0 to 1, the open interval from 0 to 1, the series has a mind of its own. This is now the period. The period of this thing is, of all these things, everything here, the period is 2L. So this is a period, and saying that that's a period means that I can now take that piece and repeat it. I can take this picture and repeat it between 1 and 3, for example. That'll give me the part from here. I repeat this, and then up here, and a jump at 2. I can repeat the thing over on the other side. Again, at the jumps, we get 0. If the problem instead had asked for a cosine series, if instead I wanted a cosine series, we start pretty much the same way. Between 0 and 1, we get the function. The cosine series, everything is even. And so the rest of the period comes by making things even. And now that's the period and can be reproduced both as many times as you want. So the question of finding the sketch to which the Fourier series converges does not require knowing any of the terms of the Fourier series. Grinding through the terms of a Fourier series can be a pain. And I will demonstrate that in just a moment by doing the next problem. But this is basically very simple. Just being a little bit careful. The second half of this problem asks to find the values at some of the places here. So we have x, the sine series, and just for convenience, we'll do the cosine series as well. Let's see, what were the values that were chosen here? -2, -3/2, 0, 1, and 2. So I go to the picture. At x equal -2, the series converges to, the sine series converges to 0. That's one of the jumps. At 3/2, I'm over here on this straight line. Halfway point, that's going to be a half. At 0, I talked about that the sine series goes to 0. At 1, it's going right through 0. And at 2, that's another jump, so 0. That was a poor choice of a problem because people who just guessed 0 for all the answers got 4 out of 5 right. If I wanted to do the cosine series instead, the cosine series over here at -2 converges to 1. At -3/2, it's at a half. At 0, it's up to 1. At 1, down to 0, and at 2, back up to 1. Would have been a better problem. The other So the other problem asks us to deal with the full Fourier series for a function given a full interval from -pi to pi. So this function, x plus pi from -pi to 0, 0 from f to 0 to pi. So the function here's my red pen. So the function here, -pi to pi, between -pi and 0, it's a straight line of slope 1. At x equal -pi, we get -pi plus pi is 0. So that goes up here up to pi, and then drops down to 0. All right. So from the definition, between -pi and pi, we have L is pi. In general, I'll make the statement that it is kinder to you if you are asked to find a cosine or a sine series because there's twice as many integrals to do with the full series. The formulas for the A's and B's in any case, so that's the full series up there at the top, the middle of the top board. A sub n, 1 over L, negative L to L, f of x, A's are cosines. So to get the coefficient of any one of the cosines, we multiply the function by that particular cosine, integrate from negative L to L and multiply by 1 over L. B sub n is the same thing with the sines. The reason to use A0 over 2 in the full Fourier series or the cosine series is so that you don't have to remember an extra formula for A0. The difference between the formulas for the full series or the sine or cosine series, sine or cosine, the function's only defined from 0 to L. And to make up for that, one has to multiply by 2. Otherwise, it's pretty much the same. I put on both sides of on these two sideboards a couple of integration formulas that I would need in doing this problem. And while it's one formula, the first thing is one always ends up having to do A0 separately. I guess I've got room for A0 here. A0, L is pi. So integral from negative pi to pi, f of x dx. That's 1 over pi. From negative pi to 0, the function is x plus pi. And then from 0 to pi, the function is 0. The integrals here, the integral of x is x squared over 2. The integral of pi is pi x, negative pi to 0. At the upper limit, the x's are 0. At the lower limit, I have to subtract the value at the lower limit, put in negative pi. That's going to give me a pi squared over 2. Negative pi there minus pi. And pi minus pi squared. Pi times pi is pi squared. So this is negative half pi squared, negative a half pi squared inside the bracket, pi squared, pi. Pi squared over pi is pi over 2. Otherwise, a sub n, 1 over pi, integral from negative pi to 0, x plus pi cosine. L is pi, so that's n pi over pi is nx dx. This is pi, not 1. Make a pi big enough so that it shows up on Jesse's screen. and then from 0 to pi it's 0. So we have this. Well, I've got a cosine of nx. There's other things are x. And so I would like to use the formulas, of course. Life is bad enough without having to do integration by parts and show that you know integration, because you've already passed that course. We don't have to test you on it again. So I need to let u, I'm going to make the substitution that u is nx, and let's see how that goes. When x is negative pi, u is negative n pi. When x is 0, u is 0. X is u over n. Pi is pi. Cosine of u, and dx, since x is u over n, dx is 1 over n du. Okay, 1 over pi. So I've got negative n pi to 0. 1 over n squared u plus 1 over n pi cosine u du. Okay, so the first thing I have is a 1 over n squared times the integral of u cosine u du. That's over here or over there. Cosine u plus u sine u. Plus 1 over n pi, cosine of u, that's sine u, n pi to 0. Okay, so 1 over n squared. Upper limit, cosine of 0 is 1. Sine of 0 is 0. Sine of 0 is 0. So at the upper limit, I have 1 over n squared times 1. At the lower limit, at n pi, I've got a negative cosine of negative n pi. The sine of n pi, sine of a multiple of pi is 0. Sine of a multiple of pi is 0. The cosine's an even function, so cosine of negative n pi is the same as cosine of n pi. And this comes out to 1 over n squared pi. 1 minus negative 1. The cosine of n pi is negative 1 to the n. B sub n, 1 over pi. B sub n, there's the formula for B sub n, 1 over L, so that's 1 over pi. again, from negative pi to 0, the function x plus pi sine of nx dx. Again, I let u be nx. X is negative pi, u is negative n pi, 0. X is u over n pi sine u 1 over n du. Again, a 1 over n squared. This time it's the integral of u du. That's sine u minus u cosine u, plus the integral of pi over n. Integral of sine is negative cosine. I'll put the negative sign there. Negative n pi to 0. Okay. So let's see. Let's see if this cleans up reasonably well. At u equals 0, the sine is 0. U times cosine, this u gives me a 0. At the upper limit, I have a negative pi over n. Cosine of 0 is 1. At the lower limit, at negative n pi, the sine is 0. I've got subtracting this, so it's another negative sign gives me a plus n pi over n squared cosine of n pi. I'm using the fact that the cosine of n negative n pi is the same as cosine of n pi, that's symmetric. Lower limit here, so I'm subtracting plus pi over n cosine of n pi. All right, so what have I got here? I've got a negative 1 over n. N over n squared, so this is pi over n. This is also pi over n. There's 2 of those, so there's 2 pi over n. Cosine of n pi is negative 1 to the n. So things collapse fairly nicely. And so I end up with my final result, a 0 over 2, a sub n cosine n x plus b sub n sine nx. A 0 somewhere over here in this mess. There it is. There's a 0. Pi over 2. I have to remember to divide that by 2, so that's a pi over 4. The sum, a sub n. A sub n is right here. 1 over n squared pi. 1 minus negative 1 to the n. Cosine of nx. And then the sign, the b sub n's, I just found b sub n. There's an n in the denominator. negative 1 plus 2 pi times negative 1 to the n sine nx. So basically straightforward. I guess the one thing that one hopes for is that we go back to being kind and asking for just a sine series or a cosine series. So you only have to go through one of these. But remember, in that case, there's an extra factor of 2. It's 2 over L times the integral instead of 1 over L. Yes, sir. N's u sine u du. N's are constants. It's the n squared. N's a constant, pi is a constant. Just, all right. What's left? This problem's not done. This problem asks, somewhere here is the problem. Then it asks to plot the function to which it converges. In this case, from negative 3 pi to 3 pi. So pi, 2 pi, 3 pi, negative 2 pi, negative 3 pi. So where the function's defined, do I still have, yeah, there's a picture of the function. So the function was defined from negative pi to pi. Where it's continuous, it's going to converge to the function. So it's going to go up here to pi and 0. But the Fourier series says, hey, a little bit to the left, it wants to be almost pi. A little bit to the right of 0, it wants to be 0. And so the Fourier series splits the difference. And the Fourier series will converge to the midpoint. And one thing is, I don't always get what my wishes are, but I always ask to grade the Fourier series problem. And while the part of it, grinding through the coefficients, is a pain, it's no more painful than most of the other problems to be graded. But the graphs are so easy to grade. And one of the things I look for, I'll tell you what my algorithm is typically. Do they have the region in the region that's defined, in particular sine or cosine? Have they got the right value from 0 to L? Does it go into the right extension, the odd or the even function on the other side? That's 2 points, 2 points. 2 points for the right values at the jumps. Show the jumps. I look for those little X's or a big dot or something. Somehow show that you know that at the jumps that it goes to the average value. And then the rest of the credit is for the periodic extension. This is the period. So this is my period. And so I simply reproduce things here on making sure that things jump. So to the right, I pick up one more period. There's a jump over there at 2 pi, and then I repeat the thing to the left. And once again, there's a jump at 3 pi. And then there's a list of values here at which one wants to know what happens. How am I? Am I right on schedule? I am. Good. So we had negative 2 pi, 0 pi, 3 pi over 2, and 5 pi over 2. One year we, it's probably on here someplace. Yeah, it's a year before, a couple of times before. We just gave a list of values, and people, a lot of students didn't try to do that by just staring at it. and not drawing the graph. And we said, oh, the results are terrible. Let's force them to get the right answers, if at all possible, by having them draw the graph. The objective are to get right answers, right? So lots of students. Negative 2 pi, that's a place where there's a jump. It jumps from halfway from 0 to pi, so this one's pi over 2. At 0, there's another jump, pi over 2. So this is an example where guessing all zeros didn't work, and that's more like the norm. At pi, here's a 0, so if you guessed zeros, you get one of them anyway. 3 pi over 2, that's halfway in between 2 pi and pi. There's another 0. No, excuse me, 3 pi over 2 is halfway between pi and 2 pi. So that's up there at pi over 2. 5 pi over 2, halfway between 2 pi and 3 pi, that's a 0. Many years ago, there was a television show that the person who did the show actually was a Roman Catholic bishop, but that doesn't matter. He, from time to time, would write things on a whiteboard, and then they go off to a podium or someplace. And when he came back, the board was always clean, which he attributed to an angel, but we all know it was a stagehand. And as I'm doing this, I wish that I had the stagehand or an angel to do this. But maybe it's just as well giving you a chance to catch up a little bit. From there we moved into separation, the partial differential equations. One of the basic thing that we have, first idea we have for dealing with partial differential equations is the idea of separation of variables. And until a couple of years ago, the way we were sequencing the course, we really we couldn't get the separation of variables onto the last exam. We wanted to have some sort of a little thing. One of the things you'll notice is the last couple of exams there wasn't such a problem. And the real separation of variables problem you had on the exam a couple of weeks ago. But these things, all we really ask for here is to obtain the differential equations. The last one that we had e to the x minus t, second partial of u with respect to x, minus x plus x minus 3 squared t to the fifth, second partial of u with respect to t equals 0. So the first step here is a couple of things. One of them, the e to the x minus t, we write that as e to the x times e to the negative t. And now the separation of variables, of course, idea is that we write u as a function x, capital X of x times a function capital T of the variable t. And as I've told my students, please try to make clear the distinction between capital and lowercase x and y, x, y, t, whatever they happen to be. So I substitute this in the partial derivative with respect to x. We hold t constant, so that's just x prime t. And then we move this to the other side. Move the other one to past the equal sign. So I have x minus 3 squared t to the fifth x times t prime. And with that, it's simple enough to to do the separation. Let's get everything on x on one side. So there's an e to the x, an x double prime, equal sign here. Let's start to put up room for quotients. To get rid of the e to the negative t, I want on the right-hand side, so I multiply both sides by e to the t. I divide by t. Now on the other side, x minus 3 squared, that's got to go to the left side. And then I have t to the 5th t, and there's t prime, and there's an x. So just a little bit of algebra to push things around, to have everything involving one variable on one side, everything involving the other on the other side. And so the argument is we have a function of x on the left side, a function of t on the right side. For those combinations of x's and t's to be equal, they must be constant. You can call the constant anything you want in this situation, but we might as well stay to the normal process of calling it negative lambda, and then we want to write down the separate. One of the things that cause people to lose credit on this problem is to stop at this point. It says find two differential equations. Write them down, two differential equations. E to the x, x double prime is negative lambda times x minus 3 cubed x, or e to the x, x double prime plus lambda x minus 3 cubed x equals 0. If I graded this, I would give full credit for this answer, but this one looks prettier, to the extent that one can call this ugly thing pretty. E to the t, t5th, t prime is negative lambda t. Squirt, because I got hung up with the 3 there. Thank you. Thank you. And let's see, t, e to the t, t to the 5th. That one looks all right. E to the t, t to the 5th, t prime plus lambda t equals 0. I corrected my error in the box as well. So one or the other of these is the differential equations. A simple problem, and the students in my sections have heard me say from time to time, don't make the easy things complicated. There's enough that's complicated at Stevens. You've all been here long enough to know that. Every now and then something comes along that isn't particularly complicated. So accept that for a gift and take it. And so we get to something complicated. And right on schedule. All right. So the last thing that on my agenda is the boundary value problem for partial differential equations. One of the things you will see on here, if you kind of browse through carefully, is that we conducted a little experiment a few years ago. On the 2010 exam, we had a problem. It was a wave equation. On the 2012 exam, we gave the same problem. On the 2014 exam, we gave the same problem. We're breaking the string. We're breaking the string. We are not repeating that problem. We had it. We did that enough times. The other thing to be said is that some of these it looks like there may even be more, maybe about the same. Some of them are wave equations, some of them are heat equations. And the basic notion is with Fourier series, if you're going to do sine or cosine, you kind of bounce back and forth. Now, last semester, we gave a full Fourier series. That means it's really time to do either sine or cosine, but we've lost the alternation, so you might get one or the other. Last semester, we did a wave equation, and so alternating wave and heat equations, it's about time for a heat equation again. And here, this is something for those of you in the room, somebody who looks at the review a year from now, this may, on the TV thing, shouldn't take that as guidance in the future. But because of that, I'm going to do the problem from at the bottom of page 5 from the 2015 S exam, which is a heat equation. The other thing is there's two kinds of ways to present for either of these, the initial conditions. One of the things is that we can, basically the idea, and I'll walk through this carefully in a moment, but the idea of solving these things is kind of a four-step process, and if you look at problems, I guess everything on pages 6 and 7, they're all the same. Just don't, you don't have mine. Those just said solve the problem. But the last couple of years, and Professor Lee was the one who really said, let's kind of help the students and guide them through the process. It makes it easier for the students, hopefully, and also easier for us to grade. So I think of this as we use the separation of variables, part A, to find an ordinary differential equations. Secondly, we use the boundary conditions and deal with the eigenvalue problem. And then solve the eigenvalue problem in the space variable for the heat or wave equation. Then we solve the corresponding equation for the time equation. And finally, applying the initial values formally leads to a Fourier series. And so we could give you a function like the 1 minus x or something like that, and say do that. But that really makes this problem, changes it from a doable monster to an really ugly monster that takes much too much time. And so if you look at all of these things, all of these all the problems from exams, this goes all the way back to 2009. Almost a decade of the times that I taught the course anyway. You see that the initial conditions are just a collection of a couple of sine or cosine functions as appropriate. But we'll make sure by the end you see how to put these together. So let me take this heat equation problem. U sub t is 3 u sub xx. X from 0 to pi, t positive. Boundary conditions. And in the case of the heat equation, for the heat equation, the thing that we're modeling here is temperature in a rod. Think of this as like a wire with nice thick insulation around the length of the wire, and then things that happen at the end. The boundary conditions saying u at 0 and t is 0 says that end of the wire or rod is being kept at a constant temperature. The boundary condition that the partial derivative is 0 says that there's no heat flowing in the lateral direction along at the end. That really corresponds to having insulation at that end. So these have physical meanings. U sub x is what it is. Let me not write it down here because I don't need it for a while. So the first step then is the separation of variable process. U is x of x times t of t. Substitute that in. I have x times t prime, 3x double prime times t. T prime over t, x double prime over x. There's a constant. The 3 can go on either side, but in general, it's in the way to some extent. If we have it there with the x, it's better off pushed off to the time part of things, and just makes dealing with it. The equation for time in the time variable is the less of an issue. And so, as usual, function of t equal a function of x, and so they must be a constant. The popular name, since we know, we choose the name from experience now, having known what's going to happen, that this is an eigenvalue problem, and the mathematicians over the years, as always, mathematicians and scientists, as you all know, say every now and then it's cool to use a Greek letter instead of a Latin one, and so we use the lambda. So we have the two differential equations. The one in x is x double prime plus lambda x is 0. The one in t is t prime plus 3 lambda t equals 0. Now the boundary conditions, u of 0 and t, that's x of 0 times t of t equals 0. If I want a non-zero solution, and the only way to satisfy the initial conditions is to find a non-zero solution, we need that the t variable not be 0 everywhere. We can live with the x variable being 0 at one point, and so we have x of 0 is 0. And similarly, from u sub x at 0 at pi and t, that's x prime at pi times t of t equals 0. Again, for a non-zero solution, we need the t function not to be 0 everywhere, and so x prime at pi is 0. So that's two differential equations and some boundary conditions. So the second step, step B, and the steps are, of course, in no sense equal difficulty, equal weight. So we have x double prime plus lambda x is 0. X of 0 is x prime at pi is 0. Again, an eigenvalue problem. Now, if you look at this this eigenvalue problem, it has the function at 0 and the derivative at pi equals 0. That's essentially the same problem, and the differential equation is exactly the same problem with x instead of y that I did an hour and 10 minutes ago, an hour and 20 minutes ago when we started. And so the two cases that lead to no solution are exactly the same. We've got here the discriminant m squared plus lambda equals 0, m plus or minus square root of negative lambda. Back then we saw that the negative discriminant, 0 discriminant, lead to no solution. Positive or 0, no non-trivial solution. So that's the problem back then. I want to do the case where I do get the solution, since I've got a pi here instead, rather than a 1 that was there before. So we just make sure that we've got things correct. The discriminant negative so negative lambda is negative alpha squared. X is C1 cosine alpha x plus C2 sine alpha x. X at 0 is C1, that's 0. X prime then is alpha C2 cosine alpha x. X prime at pi, alpha C2 cosine alpha pi equals 0 is the case here. So cosine of alpha pi is 0. That means that alpha times pi is an odd multiple, 2n plus 1, of pi over 2. Gives me alpha, the pi's cancel, 2n plus 1 over 2. Starting at 0. If you choose to write your odd numbers as 2n minus 1, then you have to start the index at 1. Right? There's certain things where you've got to have a little bit of flexibility to do things correctly and in a way that's most comfortable for you. Lambda is alpha squared. Here it's important now to get lambda correct, as you'll see in a moment. So this is 2n plus 1 over 2 squared. All of these are going to be for n equals 0, 1, 2, and so on. And finally, so I'm going to start to label these with an n, lambda sub n. And the solution, the x sub n, that came from the formula for the solution. C1 was 0, so it comes from the sine of 2n plus 1 over 2x. Sine of alpha x, we have the alpha there. And for each of the solutions, there's no reason to assume that the constant is the same. So that's part B as outlined in both of these. The problem from at the top of the page and this one, we solved the eigenvalue problem. So next we want to, for each eigenvalue, solve the corresponding differential equation for t. So the differential equation for t is up there at the top. T prime plus 3 lambda t is 0. T prime lambda is now 2n plus 1 over 2 squared times t is 0. First order differential equation for t, homogeneous, it's linear, it's separable, it's so simple that you ought to be able to write down the solution. Let's face up to the fact that that after 14 weeks of this course, you're the survivors. You ought to be able to do some of the simple stuff. So the solution here, I'm going to call it k. K sub n, e to the negative 3, 2n plus 1 over 2 squared t. And let's call that t sub n. So we have that. And let's see what else does the problem say. For each eigenvalue, give the corresponding solution to the heat equation. So now the solutions to the heat equation are x times t. We have one of these for each value of n. It's x, there's t, c sub n, k sub n, e to the negative 3, 2n plus 1 over 2 squared t, sine of 2n plus 1 over 2x. So that for each value of n is a solution to the heat equation. And now we move on to part D. And what does part D say? It says give the formal series solution. So formally, I have a solution for each value of n. I have a solution which is some constant times that ugly thing in terms of t times the sine function, and the differential equation is homogeneous, it's linear, and therefore sums of solutions are solutions. And so formally, we write this down as the sum, 1 to infinity. Now c sub n times k sub n, I put it that way. The series here is sines, and so I'm going to write my coefficient as b sub n, e to the negative 3, 2n plus 1 over 2 squared t sine alpha x. Not alpha, sine of, what is it, 2n plus 1 over 2 x. Okay, the initial condition, I get the initial condition by setting t equals 0. That's a pleasant thing to do, because when I set t equals 0, I have an exponential of e to the ugly thing times t, times 0. So that's e to the 0, which is 1. And that becomes b sub n sine of 2n plus 1 over 2x. And on the other hand, what was given at the start, I didn't write it down, but it's in there, is that this is to be 3 sine of x over 2 minus sine of 11 over 2x plus 7 sine 19 over 2x. And so these two things are supposed to be the same. Okay? Well, the objective, after all, I've got a solution here to the heat equation, to the problem. The functions are identified. All that remains is to identify the constants, the coefficients. So the goal at this step 4, step D, the last step of the process, is to identify the b's. You think about it, step A was a preparation, separation of variables. Step B, the eigenvalue problem, found the solution, the x component of the solution. The next step, step C, found the t component of the solution. What remains are the coefficients. And here it's just a matter of matching. I want to get something with sine of x over 2. Well, in there I get sine x over 2 from the n equals 0. This starts at 0. These both start at 0 because I chose to start my indices at 0. Everything's got to be consistent, especially if I want to have a solution. So the n equals 0 term gives me sine of 1 over 2. This tells me then for n equals 0, b0 is 3. That gives me that term. Next, the sine of 11 pi over 2. I get sine of 11 pi over 2 from n equal 5. N equal 5, and then b5, n equal 5, yeah. b5 is negative 1. The last thing, sine of 19 over 2. I get 19 over 2 from n equal 9. B9 is 7. All other b sub n's are 0. And so I get to write down the final solution to the problem. U is first term, n equals 0 term. First term in here, 3. N equals 0, 3. N equals 0 is an e to the negative 3, 1/2 squared t sine 1/2 x. The next term is the 5 term, minus 1, e to the negative 3, 11 over 2 squared t sine 11 over 2 x. Finally, 7 e to the negative 3, 19 over 2 squared t sine 19 over 2 x. Some complications? Yes. I made the comment a little while ago that accept the fact that occasionally something's simple because there's lots of complicated stuff at Stevens. Here's an example. At the end of your technical courses, things that build up and suddenly you find something which combines a whole bunch of things. But that's kind of the nature of our business of trying to be in a position, as you all hopefully will be in a few years, to deal well with problems in the particular field of your interest, and to use mathematics as a tool in dealing with those fields. And so, if there are any questions, I will have a try to do that. If not, I hope that all of you will do extremely well on the exam on Tuesday. Once again, is Devin Belmar here? Devin, did Devin come in? Could I just see him for a minute? Thank you.